Hi. Can you hear me? Cool. And I should say the only reason that this talk isn't recorded is because I submitted an earlier version of this paper to a conference and wasn't supposed to have any public sort of presentation of it in other venues. So sorry that that's not a very exciting reason. Okay. Open source learning with bargaining, which is a slightly less grandiose title than the original. Okay, so open source learning is a model for multi-agent reinforcement learning where agents are highly transparent to each other. Let me start this timer, actually. Okay, so the reasons I'm interested in this are one, to understand better the behavior of reinforcement learning agents who are highly transparent to one another, and then to try to leverage this transparency for better cooperation. And I will skip this in the interest of time. So first, I'll say a little bit in the way of background and motivation about cooperation among AI systems, and then tell you about the particular contribution. So I think actually probably the first part is more important, and this open source learning is just kind of a concrete example of how one might proceed with research on cooperation among AI systems using contemporary tools. Okay. Cooperation. So the ultimate goal here is to make transformative AI, which I'll call TAI from now on, go well. And of course, the AI safety community is doing a lot of thinking about problems of alignment and control. But cooperation is also important, and at least depending on your definition of alignment, may fail even if alignment and control work. So as an example of a kind of failure mode, that we might run into even if we largely solve these alignment and control problems is a social dilemma, which many of you are probably familiar with. So a social dilemma is a game where everyone is better off if everyone cooperates than if everyone defects. But individually, people have reason to defect. And examples that you're likely familiar with are the prisoner's dilemma, chicken, stag hunt. And moreover, these model many unfortunate real-world situations that we'd like to prevent. So arms races, tragedies of the commons, and so on. And again, we may end up with mutual defection in these cases, even among AI systems, which are largely aligned with human interests. Okay, so what does this have to do with this transparency? So machine agents, at least in principle, can be highly transparent to one another. So in particular, in principle, they can share their source codes with one another. If they're made out of neural networks, they can share their parameters with one another. Of course, the in principle is very important here because a transformative AI system will be an extremely complicated object, and it may be prohibitively difficult for agents to verify these various aspects of one another's internal workings. But nevertheless, because of the possibility that agents will at least be much more transparent to each other than, say, humans are to one another, and the interesting properties of transparency with respect to cooperation, I think it's still worth studying. So transparent agents can better achieve cooperation in some cases, so I'll make this a bit more concrete when I talk about this open source game theory later, but this is somewhat intuitive. Though I don't mean to argue that transparency is kind of uniformly better than non-transparency. For instance, agents who are transparent to one another can also credibly threaten each other, or threaten each other much more credibly than non-transparent agents. But whether it's a uniform improvement or not, it's an interesting thing to study and try to make go better. So, and of course, there's plenty of existing work on promoting cooperation in social dilemmas among reinforcement learners under varying degrees of transparency, and I see the contribution of the work that I'll describe as helping to map out this space of possibilities for achieving cooperation among reinforcement learners, and I'll be looking at a case where the agents are highly transparent. Okay, so this next page is a table with a lot of text that's not so important to read through. The upshot is that I've listed some recent papers on cooperation among deep reinforcement learning agents, where the agents are more to less opaque. So in this first case, this consequentialist conditional cooperation, the agents can't see one another's actions. They can only observe their sort of local state and their own rewards, and they have to infer based on the rewards that they're getting whether they're being defected against or not. And then if they have sufficient evidence that they're being defected against, they try to punish their counterpart. So that's a case of low transparency. Whereas I'll tell you about a case of high transparency, where the agents can see all kinds of things about one another, in particular the parameters of their policy and the source codes of their learning algorithm. And the intuition is that under greater transparency, you can detect and punish defections much more efficiently than in the opaque case. Okay, so open source learning. Again, the setting is multi-agent reinforcement learning, so we'll just look at a case with 2 agents. And these 2 agents are trying to learn policies which give them high long-term reward in some sense. This is an example of a multi-agent reinforcement learning game. Basically, you have this blue player and this red player, and they're running around trying to gather fruit, which gives them reward, and they're trying to learn policies which allow them to gather a lot of fruit in the long term. So incidentally, this was an example of a so-called sequential social dilemma that was proposed a couple years ago. But this is just to make things more concrete. But the main idea of open source learning is as follows. So the players will be jointly optimizing some kind of compromise value function rather than trying to optimize their individual value functions, and punish their counterpart if they see that they're not updating their policies accordingly. So we would like to make this into really more or less a single agent reinforcement learning problem, where the agents are jointly optimizing some value function that represents a compromise between the things that they want. Only, of course, the agents will have reason to defect and try to go off and do things that get even more reward for them. So we need to have some mechanism for detecting and punishing defections from the optimization of the compromised value function. Okay, so making this a little more precise, we have a welfare function, so that's what I was just calling the compromised value function. This is what it's called in the game theory literature. So this represents some compromise between players' individual value functions. For the purposes of the talk, I'll actually just take this as given. This could arise from some kind of cooperative bargaining setup. So, for instance, it could be the Nash welfare function, which I'll display on the next line. It could also, the players could also agree upon this function as in an alternating offers game, but it's not so important where this welfare function comes from for the purposes of this talk. It's just something that the agents are satisfied to jointly optimize. Okay, and then learning algorithms which are transparent. So the learning algorithm is the thing that takes the agent's history of observations and updates their policy in a direction that they think will give them more reward in the long term. So a transparent learning algorithm is one that can see the counterpart's policy parameters and source code in addition to the history of observations. And then the punishment regime, remember I said that you need to have some way of punishing your counterpart if they don't update towards the maximum of the welfare function. So this in particular will be attempting to minimize your counterpart's payoffs over some time horizon. Okay, so I don't have time to walk through the details of this Nash welfare function, but basically this is one example of a welfare function that has some nice properties, and it basically maximizes the product of each player's gains from bargaining. So this is one example of something that the players might agree to optimize. Okay, program equilibrium. So this is the way these transparent learning algorithms will decide what updates to return. So the main idea of program equilibrium is instead of playing a game where you and I simultaneously submit actions, we simultaneously submit computer programs that will act on our behalf. And critically, those computer programs can see one another's source codes. And this can lead to basically more cooperative outcomes because you can anticipate, you can submit a computer program that will see that your counterpart's program defects against you and then defect accordingly. And this makes the submission of computer programs that cooperate with each other in equilibrium. So in this paper, I use my colleague Casper Osterheld's epsilon-grounded Fairbot, which uses a counterpart's source code to simulate their response to itself. And the epsilon-grounded part is that with some small probability epsilon, you have to take some default action to avoid an infinite recursion, because of course, my counterpart's program will be, in general, simulating me as well. So, okay, so this is all defined for just a normal form game like the Prisoner's Dilemma or whatever, but we can identify, this is just a diagram of epsilon-grounded Fairbot playing against another epsilon-grounded algorithm, but I don't have time to walk through that. Okay, so here we identify cooperation and defection with updating towards or not towards the estimated optimum of the welfare function, which I'll call the bargaining solution. So basically just use something very similar to epsilon-grounded Fairbot to choose policy updates, again, where the actions cooperation and defection correspond to cooperative or uncooperative policy updates, and punish if you see that your opponent's source code implies that they will defect. That is not update towards the bargaining solution. Okay, so a picture of this real quickly. So we have this surface represents the welfare function as a function of the player's policies. Pi 1 is the first player's policy, pi 2 is the second player's policy. The cooperative thing to do is go towards this estimated bargaining solution at the top of the surface, and this black dot is where the policies currently are. So the cooperative thing to do is for player 1 to move towards the bargaining solution, player 2 to move towards the bargaining solution, and altogether they go towards the optimum of the welfare function, or the estimated optimum. On the other hand, if player 1 defects, this will, with high probability, be detected and punished by player 2. Okay, obviously, you've probably thought of many problems that need to be addressed here. One is enforceability, so it might be the case that you can do better than cooperating, even if your counterpart is trying to punish you. Another is, of course, I've made very strong assumptions about the agent's ability to verify various things about each other's internal workings. And so relaxing those assumptions is, of course, a very important part of getting something that looks kind of like this to work in the real world. It would also be nice to look at the empirical performance of open source learning algorithms and compare the ability of these to promote cooperation with other approaches that make less use of transparency. So I have some thoughts on these, but there's lots more to do. Okay, and lastly, at EAF, we're working on a research agenda that is about cooperation among TAI systems. So there's some stuff related to this open source interaction, but there's lots more as well. Feel free to reach out to me if you'd like to chat about it, or look out for it. Hopefully it'll be public by the end of the year. Okay, that's all I have.
Cool. So I guess a question I'm curious about to start with is the set of assumptions about how transformative AI goes down that are required for this work to matter. Like which scenarios, like what assumptions are we making about what scenario we're in for this stuff, do you think?
Yeah, so I mean, I guess I should say it first. Like generally, I don't see like this particular thing like being put into the transformative AI. But what sort of assumptions need to hold for some kind of open source interaction to work out? Well, it needs to be at least a bipolar scenario. So there need to be more than one AI in the mix. And of course, the big thing is that it's even possible for agents to verify their counterparts' internal workings to the extent that they think that something like this is in their interest. And of course, far from obvious that will be true. Yeah.
Maybe this is a reason for us to want to differentially advance, whatever technologies are required to make verification easier. So we make it easier for AI systems to verify properties of other AI systems. Do you think this overall seems like a good idea as a result of these considerations?
Yeah, the fact that transparency can promote cooperation is definitely a reason in favor of that. As I tried to say earlier, it's still not obvious that overall agents being highly transparent to one another is a good thing because of this notion of being able to make more credible threats and so on. My intuition is that all things considered, it's still good that agents be able to be highly transparent to one another, but that's something I'm very uncertain about and seems like an important question to answer. Yeah.
I guess another question is if we already have these systems that are operating in the real world, I'm curious how much of this kind of research we can just defer to them. When we're making these really powerful systems and we say, hey, there's a couple papers on open source learning algorithms or whatever, can you improve that research area? I'm curious whether you feel this research is particularly important to develop before we have powerful enough technologies to help us with this research, or I'm curious how you think of it.
Yeah, well, I think one point in favor of it being important to do early is the possible path dependencies that you pointed to in your last question. So if we need to differentially advance sort of technologies for validation, verification, and so on, that might be something that, that might be a reason in favor of doing this earlier rather than to deferring to systems later when it's already sort of too late.
Cool. I guess another thing is, it kind of seems to me that there were many places in your talk where advances in various other fields would be helpful for making this stuff work out. Mm-hmm. So, one that seems right is zero knowledge proofs seem like they would help with some of the situations where you don't want to share your source code with your adversaries who are, where you don't want to share your AGI's source code with your adversaries who are making their AGI because you don't want to save them. I'm curious if there are other examples to you of, outside fields which would be helpful for making this kind of stuff work out.
Yeah, I think that the one you mentioned is right, and verification more generally, and also understanding sort of the methods for better interpretability of machine learning systems might also be important, and also seems kind of broadly good anyway. But yeah, I think the ones that you mentioned are the natural ones to look into.
Cool. I guess one final question here from me. I'm curious how you plan to prioritize doing further work in this particular formalism, mm-hmm. And getting a deeper theory of what happens in this formalism versus coming up with richer formalisms. There's two kinds of ways you can try and develop a research area. I'm curious how you're thinking of that here.
Yeah. I think there are considerations pointing in both directions, especially because I mentioned I don't think that this particular framework is all that realistic. I think that there are maybe this is sort of another reason to develop other frameworks that are maybe more realistic. And I tend to think generally that there are fairly quickly diminishing marginal returns to research in some kind of narrow formalism that you're not confident is really that realistic in the first place. On the other hand, I think that you can just learn a lot by studying a formalism, even if it's not even if it's highly idealized. And I mean, I think for sort of instrumental reasons, it's hard to kind of establish an academic subfield if you come up with lots of frameworks but never really deeply explore any particular one. So yeah, I think that I'd probably be excited to, all things considered, keep working on this and try to get better answers to some of the questions I listed.
Great.
Yeah.
Okay, thank you both. So there's a particularly good question from the audience that I want to ask you, Jesse. Someone is wondering, what assumptions do you make about the length of the co-learning phase? In reality, the two agents might only get to interact a small number of times. So do the results hold then?
Right. So, so actually, in the paper, everything, all the utilities are defined as these kind of limit of average reward, kind of infinite horizon objectives. So that is not because I think that that's like a realistic approximation to the lengths of times over which these agents are going to be interacting, but really just so that the quantities are easy to define. But I think that's also sort of typical of reinforcement learning theory. It's hard to say much about finite time horizons in general. So the short answer to your question is that the few things that I proved in the paper are for these kind of very unrealistic asymptotic regimes. Yeah.
Okay, great, that makes sense. Second question is, do you think that mutual cooperation is the only equilibrium in your setup?
Probably not. But I imagine that it's the social welfare maximizing equilibrium. Yeah, so one problem with this program equilibrium stuff in general is that like there are many equilibria of program games. But you may be able to weed out like many of the equilibria on the basis that like there's only a few that maximize social welfare. Yeah.
Great.